Hello everyone. Today we are going to analyze this frame using Kani's method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column CD. Also, there is a beam BC. In the column AB, there is uniformly distributed load 12 kN per meter acting for the full span. In the beam BC, there is a point load 20 kN acting in the center. In the column CD, there is a point load 27 kN acting at 1 meter from the point D. The moment of inertia for the span AB is I, for the span BC is 3I, and for the span CD is 1.5I. Length of the column AB is 4 meter. Length of the beam BC is 4 meter. Length of the column CD is 3 meter. In the points A and D, there are fixed supports. This frame is a survey type frame because the columns AB and CD are having different lengths. Now let us find the fixed end moments in the column AB. In the column AB, there is UDL 12 kN per meter acting for the full span. The formulas for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Here W is 12, L is 4. When we apply these values in the formulas, we are getting M of AB and M of BA. Now let us find the fixed end moments in the beam BC. In the beam BC, there is a point load acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. Here W is 20, L is 4. When we apply the values in the formulas, we are getting M of BC and M of CB. Now let us find the fixed end moments in the column CD. In the column CD, there is an eccentric point load 27 kN. The formulas for the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. Here W is 27, A is 2, B is 1. When we apply the values in the formulas, we are getting M of CD and M of DC. We know that this frame is subjected to survey. In the columns AB and CD, there are loads. So we have to find the story moment. To calculate the story moment, we have to find the horizontal reactions in the points B and C. We can find the horizontal reactions using the loads and the fixed end moments. First, let us find the horizontal reaction in the point B, HB. Since in the column AB we have symmetrical loading, we can easily find HB. For that, we have to divide the total load by 2. Here the total load is 12 into 4. So 12 into 4 upon 2, we will get HB. HB should be acting towards the left side. Now let us find the horizontal reaction in the point C, HC. For that, I am going to take movement about D. In this case, I am moving towards the right hand side. clockwise will be positive and anti-clockwise will be negative. HC is acting towards the point D in the clockwise direction, so it will be positive and the distance is 3 meter, so 3 HC. The point load 27 kilonewton is acting in the anti-clockwise direction, so it will be negative and the distance is 1 meter, so minus 27 into 1. This movement is acting in the anti-clockwise direction, so it will be negative. This movement is acting in the clockwise direction, so it will be positive. Finally, we are getting HC. HC should be acting towards the right side. Now, let us find the story moment. The formula is SR HR upon 3. SR is the story shear. To find the story shear, we have to add the horizontal reactions in the points B and C. The reaction in the point B is acting towards the left side, so it will be positive. The reaction in the point C is acting towards the right side, so it will be negative. When we add these two values, we will get 17. HR is the reference height. In this frame, there are two columns, column AB and column CD. We have to select one of the column as the reference column. Let us take the column AB as the reference column. The height of the column AB is 4, so the reference height is 4. After calculating this, we are getting the story moment, which is equal to 22.6667 kilonewton meter. In the Kani's method, we have to find the rotation factor. To find the rotation factor, we have to calculate the stiffness. Let us see the formulas to find the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. First, let us find the stiffness for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BA is 4. Let us apply that. Finally, for the stiffness of BA, we are getting EI. Now let us find the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous. If the fair end is continuous, the formula for the stiffness is 4EI upon L. Length of BC is 4. Let us apply that. The moment of inertia for BC is 3I. So instead of I, we have to apply 3I. For the stiffness of BC, we are getting 3EI. Now let us find the stiffness for CB. For that, from the joint C, we have to look at the point B. The point B is continuous. If the fair end is continuous, the formula for the stiffness is 4EI upon L. Length of CB is 4. Let us apply that. The moment of inertia for CB is 3I. So instead of I, we have to apply 3I. Finally, for the stiffness of CB, we are getting 3EI. Now let us find the stiffness for CD. For that, from the joint C, we have to look at the point D. In the point D, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of CD is 3. Let us apply that. The moment of inertia for CD is 1.5I. So instead of I, we have to apply 1.5I. Finally, for the stiffness of CD, we are getting 2EI. Now, let us find sigma k. In the joint B, we have found two k values. Let us add both of them. After adding, we are getting 4EI. In the joint C also, we have found two stiffness values. Let us add both of them. After adding, we are getting 5EI. Now let us find the rotation factor. The formula is minus 1 upon 2 into k upon sigma k. Using the formula, we can find the rotation factor values. We know that this frame is subjected to sway. In this case, we have to find the displacement factor for the columns BA and CD. Since both of the columns are having the different lengths, we have to use this formula. Let us see how to apply the values inside this formula. Let us make one table. First, let us enter story. In this frame, there is only one story. In this story, we have the columns BA and CD. Previously, we have calculated the stiffness for BA and CD. Let us enter them. Now, let us find the C values. The formula for C is reference height upon column height. We have selected the column AB as the reference column and the reference height is 4 meter. So for CBA, the reference height is 4. The height of column AB is 4. 4 upon 4, we will get 1. For CCD, the reference height is 4. The column height is 3. 4 upon 3, we will get 1.3333. Let us enter these values. Now let us find Kc. When we multiply these two values, we will get EI. When we multiply these two values, we will get these. Now let us find C square. When we square 1, we will get 1. When we square this value, we will get these. Now let us apply the values of M. If the column has fixed end, the value of M is 1. If the column has hinged end, the value of M is 3 upon 4. Right now, both of the columns having the fixed ends. So for the columns BA and CD, the value of M is 1. Now let us find MC square K. For that, we have to multiply the values of M, C square and K. When we do that, we are getting these. Now let us find sigma mc square k. For that, we have to add these two values. After adding, we are getting these. Now let us find the displacement factor. The formula is minus 3 upon 2 into kc upon sigma mc square k. We have already calculated kc and sigma mc square k values. After applying the values inside the formula, we are getting the displacement factors. In the Kani's method, in the joints, we have to make boxes like these. Now let us enter the fixed end moments. Here MFAB, here MFBA, here MFBC, here MFCB, here MFCD, and here MFDC. In the joints, we have to add the fixed end moments. When we add these two moments, we will get 6. When we add these two, we will get 4. Now let us enter the rotation factor values. The rotation factor for BA is minus 0.125, for BC is minus 0.375, for CB is minus 0.3, and for CD is minus 0.2. Now let us enter the displacement factors. For the column BA, the displacement factor is minus 0.3293, and for the column CD, the displacement factor is minus 0.8780. In the Kani's method, in the joints, we have to find the rotation contributions. In the joint B, there are two rotation contributions, M-BA and M-BC. In the joint C also, there are two rotation contributions, M-CB and M-CD. In the end of the columns, we have the displacement contributions. In the point A, we have M'-AB, and in the point D, we have M'-DC. The formula to find the rotation contribution is summation of rotation or displacement contributions at a fair end plus summation of fixed end moments into rotation factor. Now let us find M'-BA. M'-BA is located in the point B. For the point B, the fair ends are the point A and the point C. In the point A, initially the value of M'-AB will be 0. Also in the point C, initially the value of M'-CB will be 0. So for the summation of rotation or displacement contributions at a fair end, we have 0 plus 0. The summation of fixed end moments is 6. The rotation factor for BA is minus 0.125. Finally, for M'-BA, we are getting minus 0.75. For M'-BA and M'-BC, all of the values will be same except the rotation factor. The rotation factor for BC is minus 0.375. After the calculations, we are getting M'-BC, which is equal to minus 2.25. Let us apply the values of M'-BA and M'-BC. Now let us find M'-CB. M'-CB is located in the point C. For the point C, the fair ends are the point B and the point D. The rotation contribution in the point B is minus 2.25. In the point D, initially M'-DC will be 0. So for the summation of rotation or displacement contributions at fair end, we have minus 2.25 plus 0. The summation of fixed end moments is 4. The rotation factor for CB is minus 0.3. For M'-CB, we are getting minus 0.525. For M'-CB and M'-CD, all of the values will be same except the rotation factor. The rotation factor for CD is minus 0.2. After calculating, we will get M'-CD, which is equal to minus 0.35. Let us enter the values of M'-CB and M'-CD. Now we are going to find the displacement contributions. It is a little tricky to find them, so we can use this formula and find them. The formula is story moment plus M'-BA into CBA plus M'-CD into CCD into displacement factor. In the formula, let us apply the values. The story moment initially we have calculated. Let us apply that. M dash BA is minus 0.75, CBA is 1, M dash CD is minus 0.35, CCD is 1.3333. The displacement factor for the column AB is minus 0.3293. After the calculation, we are getting M double dash AB. For M double dash AB and M double dash DC, all of the values will be same except the displacement factor. The displacement factor for the column CD is minus 0.8780. After the calculation, we are getting this. Let us apply the value of M double dash AB and M double dash CD. We have finished the first iteration. Now let us start the second iteration. Now let us find M dash BA. Now in the point A, we have the displacement contribution. Also in the point C, we have the rotation contribution. The summation of the fixed end moment is 6. The rotation factor for BA is minus 0.125. After the calculation, we are getting M dash BA. We know that for M dash BA and M dash BC, all of the values will be same except the rotation factor. The rotation factor for BC is minus 0.375. Finally, for M dash BC, we are getting 0.595. Let us apply the values of M dash BA and M dash BC. Now let us find M dash CB. The rotation contribution in the point B is 0.595. The displacement contribution in the point D is minus 18.833. The summation of fixed end moments is 4. The rotation factor for CB is minus 0.3. After the calculation, we are getting 4.271. We know that for M dash CB and M dash CD, all of the values will be same except the rotation factor. The rotation factor for CD is minus 0.2. After the calculation, we are getting 2.847. Let us apply the value of M dash CB and M dash CD. Now let us find the displacement contributions. In this formula, let us apply the values. Let us apply the story moment. M dash BA is 0.198, CBA is 1, M dash CD is 2.847, CCD is 1.3333. The displacement factor for the column AB is minus 0.3293. After the calculation, we are getting M double dash AB. We know that for M double dash AB and M double dash DC, all of the values will be same except the displacement factor. The displacement factor for the column DC is minus 0.8780. After the calculation, we are getting M double dash CD. Let us apply the values of M double dash AB and M double dash CD. Now we have finished the second iteration. Let us start the third iteration. Let us find M dash BA. For that, we have to add these three values and then multiply with the rotation factor for BA. When we do that, we are getting minus 0.186. The rotation factor for BC is minus 0.375. For M dash BC, we are getting minus 0.559. Now let us find M dash CB. For that, we have to add these three values and then multiply with the rotation factor for CB. When we do that, we are getting 5.99. The rotation factor for CD is minus 0.2. For M dash CD, we are getting 3.993. Let us apply the values of M dash CB and M dash CD. Now let us find the displacement contributions. In the formula, let us apply the values. Let us apply the values of CBA, CCD and story moment. M dash BA is minus 0.186. M dash CD is 3.993. The displacement factor for the column AB is minus 0.3293. For M double dash AB, we are getting minus 9.156. For M double dash DC, we have to apply the displacement factor for the column CD. Finally, we are getting M double dash CD. Let us apply both of the values. Now we have finished the third iteration. Let us start the fourth iteration. Now let us find M dash BA. For that, we have to add these three values and then multiply with the rotation factor for BA. When we do that, we are getting minus 0.354. The rotation factor for BC is minus 0.375. For M dash BC, we are getting minus 1.063. Let us apply both of the values. Now let us find M dash CB. For that, we have to add these three values and then multiply with the rotation factor for CB. When we do that, we are getting 6.442. The rotation factor for CD is minus 0.2. For M dash CD, we are getting 4.295. Let us apply both of these values. Now let us find the displacement contributions. In the formula, let us apply the values of CBA, CCD and story movement. The value of M dash BA is minus 0.354. The value of M dash CD is 4.295. The displacement factor for the column AB is minus 0.3293. After the calculation, we are getting M double dash AB. The displacement factor for the column CD is minus 0.8780. After the calculation, we will get M double dash DC. Let us apply both of them. Now we have finished the fourth iteration. Let us start the fifth iteration. In the fifth iteration, here I have found the rotation contributions. Here I have found the displacement contributions. Here I have done the sixth iteration. Here I have calculated the rotation contributions. Here the displacement contributions. I am going to stop in the sixth iteration because in the fifth and sixth iterations I am getting approximately equal values. Now let us see the formula to find the final moments. Fixed end moments plus 2 into rotation contribution at near end plus rotation contribution at far end plus the displacement contribution. Let us make a table. In the table, first let us enter all of the members, then the fixed end moments, then 2 into near end rotation contribution, then far end rotation contribution, then the displacement contribution, then the final moments. The near end rotation contribution for AB and DC will be 0 because in the fixed ends there will be no rotation contribution. So 2 into 0 The near end rotation contribution for BA is minus 0.412, for BC minus 1.237, for CB 6.568, for CD 4.379. Then using the arrows we can enter the fair end contributions. Now let us apply the displacement contributions. The displacement contributions will be available only on the columns. So it is only available in the columns AB and CD. For the beam BC, it won't be available. So for BC and CB, there is no displacement contribution. For AB and BA, the displacement contribution is minus 9.251. For CD and DC, the displacement contribution is minus 24.666. Now let us add these four values and find the final moments. After adding, we are getting the final moments. In the joint B, for BA and BC, we got different values. These values are slightly different. We can take average of these two, or we can select any one of them to be same. I am going to keep the moment for BA and BC as 5.92. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got positive value. That means it is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anti-clockwise direction. For MCB, we got positive value. That means it is acting in the clockwise direction. For MCD, we got a negative value. That means it is acting in the anti-clockwise direction. For MDC also, we got a negative value. That means it is also acting in the anti-clockwise direction. Now we are going to find the reactions. By taking moment about B, we can find HA. By applying the rule sigma H is equal to 0, we can find HB. Then by taking moment about C, we can find VB. Then by applying the rule sigma V is equal to 0, we can find VC. By taking moment about D, we can find HC. By applying the rule sigma H is equal to 0, we can find HD. Using the reactions and loads, we can make the shear force diagram. Using the formulas, we can make the free movement diagram. Using the direction of the end movements, we can make the end movement diagram. Then we can combine the free movement diagram and end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.